Hi, everyone. Thank you all for attending. I'm Michael Hammer. I'm not currently at an institution, but I'll be starting a postdoc at Asia A as soon as Taiwan lets me in the country. And today for my research spotlight, I'll be talking about my work with Min-Kai Lin, Paola Pinilla, and Caitlin Crowder on whether vortices should be more common in observations of protoplanetary disks. So, so are vortices common in protoplanetary disks? We think the answer to that is no. If we go back to Ninka's gallery of resolved transition disks and ignore all the cases that might be limb brightening, we'll see that asymmetries that could be candidate vortices are much less common than features like gaps and rings. Now, overall, only about a quarter of these disks have clear large-scale asymmetries. And among these dozen or so cases, only two of them have a normal gap associated with an asymmetry. That would be HD 1353-44B and V12 47 ORI. Most of the rest have cavities, but these are the only two I'm aware of that have both a gap and one or more asymmetries, which is the type of structure we would expect if a planet forms in the middle of the disk and triggers a vortex. So if we care more about the large-scale asymmetries that are vortices generated by gap-opening planets, which at least I care more about, then those seem quite rare. Now, how did these asymmetries form to begin with? Well, one of the most favorable ideas is that they are vortices generated by gap-opening planets, but for that to be true, the planet must have formed relatively recently, and to accurately model what the asymmetries look like in observations, you may need to incorporate the planet's growth time into your simulations. Now we can watch planets generate asymmetries by running hydrodynamic simulations of a gap opening planet in a disk of gas and dust. In this simulation, we place a Jupiter mass planet in a disk with a very low viscosity, but we introduce the planet slowly over 1,000 orbits. Now, when the planet reaches a fifth of a Jupiter mass, about 300 orbits, it makes the disk unstable and triggers a vortex. Now, the vortex has a width of more than 180 degrees, and it lasts about 1,500 orbits, which is 5 times shorter than what would happen if the planet's growth wasn't taken into account. Now, if we develop a synthetic image based on the dust in the vortex, then we'll see it matches up with observations of HD 1353-44b pretty well. Now, they both have azimuthal extents of about 180 degrees, and they also both have off-center peaks. Now, if we hadn't incorporated the growth of the planet, then the vortex would be way too compact to resemble the crescent in HD 1353-44b, and it also wouldn't have an off-center peak. So why do compact and elongated vortices look so different? Well, they are different types of vortices. Now, if the planet grows instantly, you form a compact vortex that's well described by the relatively new Gaussian model. And if the planet grows slowly, you form an elongated vortex that's well described by the classic GNG model. Now, recently, Serval and Barge studied both types of vortices, and they found that the difference between the elongated and the compact models wasn't actually so much the extent of the vortex, but really the minimum Rossby number in the vortex, which is just the amount of vorticity in the vortex. If the minimum was less than minus 0.15, then the vortex would be compact. If it's more than minus 0.15, so if it's less negative, then it would be elongated. Now it's relatively easy to see why a slowly growing planet produces a weaker vortex. When the planet grows slowly, the initial set of vortices instead have elongated Rossby numbers. And when these vortices merge, the final vortex also has an elongated Rossby number. And it never develops a clear vorticity minimum at its center. As a result, when the planet continues to grow, it can't strengthen the vortex or cause the Rossby number to drop as much as it does when the planet grows instantly. Now, why do elongated vortices have elongated azimuthal extents in the dust, and why do they have off-center peaks? Both of those features happen because the dust circulates around the vortex. So just like with normal vortices, the increase in density at the edge of the vortex creates a pressure bump that, when combined with the rotating velocity fields of the vortex, naturally traps dust. However, that is where the similarities end. If I add contours to both vortices, you'll see that the compact vortex has nice elliptical contours and a very smooth pressure bump, while the elongated vortex does not. As a result, once the vortex collects dust, that dust has no reason to spiral inward to the center like it would in a normal vortex. So what happens instead? Instead, the dust circulates around the vortex, as you can see here, for 1 centimeter and 3 millimeter size grains. Now, this motion leaves the vortex nearly as elongated in the dust as it is in the gas. And furthermore, it also leaves the peak in the dust density off-center most of the time. And this creates a big distinction between compact and elongated vortices. So overall, actual vortices appear elongated. There aren't too many vortices in protoplanetary disk observations, and elongated vortices have relatively short lifetimes. Now that seems consistent, but do elongated vortices always have shorter lifetimes? The answer is not for lower mass planets. Now, besides trying lower mass planets in a more recent paper, one other thing we changed was how the planet grows. Now, having the planet grow a Jupiter mass doesn't make sense if we don't remove a Jupiter mass worth of gas from the disk. A better approach would be to have the planet accrete material from the disk itself so that the gap edge self-consistently evolves with the growth of the planet. In this simulation, the planet grows to about 0.2 Jupiter masses. And like the other cases, the initial vortex only lasts a little more than 1,000 orbits. But this time the vortex can reform. And in fact, that happens at least 3 times at about 2,600 orbits, at about 3,150 orbits, and again at 3,660 orbits. And in total, the vortex survives more than 5,000 orbits and is still alive at the end of this movie, which gives it a way longer lifetime than the Jupiter mass case. Now, one other important thing to note is that even though the gas vortex dies out and reforms, the dust asymmetry never dies out until after the end of the last vortex.
5 minutes left.
Thanks. So the total lifetime is the start of the first gas vortex until the end of the last one. And because of the later generation vortices, the two lower mass planets we simulated generate vortices with lifetimes over 6,000 orbits, while the two higher mass planets generate vortices that don't even reach 2,500 orbits. Now, the elongated vortices have shown die out by eventually spreading into a ring, but why does that happen? Well, viscosity is one way to kill a vortex, but you need at least an alpha of 10 to the minus 4 for that to happen quickly. And the movies I've shown so far don't actually have that high of a viscosity. Instead, the elongated vortices I've shown actually die because of shocks from the planet's spiral waves. But that doesn't always happen. If we increase h of r to a very high 0.08, then the vortex hardly changes after it forms. It does decay, but that happens, now it does decay, but it happens very slowly because the shocks from the planet's spiral waves are too weak to dissipate it. As a result, the vortex never spreads into a ring, and it's still alive even at the end of this movie. Now, all of the simulations I've shown so far were for relatively low viscosity. Do these trends still hold up with a higher viscosity? Well, no, not really. Viscosity is what kills the vortex, so the vortex lifetimes are still much shorter. Now, these are all the vortex lifetimes with the viscosity I've been using throughout this presentation. Most of them are above 2,000 orbits, but with a 10 times higher viscosity, none of the lifetimes even reach 2,000 orbits, regardless of what the planet mass is. So, should asymmetries be more common in protoplanetary disk observations? Now, at least in some cases, it seems like the answer is yes. It's not easy to tell why, but if we can figure that out, then that might help us constrain planet and disk properties. And we attempted to quantify this idea by looking at a sample of gaps in torus that were associated with planets that are massive enough to trigger vortices. So we could estimate the chance of observing a vortex in these systems by assuming a vortex lifetime of 1,000 orbits and a cluster age of 2 million years. So in this case, 1,000 orbits would be about 10% of the cluster's lifetime, and or the cluster's age. And some of the other cases are the gaps are much further out, so the percentages go up. And the last few cases, the gaps are really far out, so you expect a vortex in a significant fraction of the disk lifetime so far. And that was just for 1,000 orbits. Now, in our study, we found that vortices have characteristic lifetimes of 2,000 orbits, and in some cases even 6,000 orbits. Now, these percentages are high enough that we expect at least one of these systems to have a vortex, but none of them do. And if we assumed a lifetime of 3,000 orbits, then we expect like half of them to have vortices. So why don't any of them have vortices? The simplest explanation might be that disks actually do have a moderate amount of viscosity. Another simple explanation might be that they might be massive enough to trigger vortices if they're stationary, but if they're migrating, that increases the minimum mass needed for them to trigger a vortex. For the ones in the outer disk, because they've had so few orbits so far, maybe they just haven't triggered a vortex yet, and they will eventually. Besides that, in terms of physical effects, two recent works showed that certain cooling time is optimal for killing the vortex, and that may be a realistic value in the outer disk. Self-gravity is also can be important, can also weaken vortices. It can apply for a relatively wide range of relatively low masses, but it's not as strong of an effect for relatively low masses. And it's also been suggested that dust feedback can kill vortices, but that doesn't seem to hold up in 3D. So to summarize, Elongated vortices are characterized by wide azimuthal extents and off-center peaks. If H over R is less than 0.06, lower mass planets actually generate longer-lived asymmetries because the vortex can reform. With very large H over R, vortices are long-lived because the shocks from the planet that normally kill it are too weak to do so. Because of these trends, it should be better to test vortex killing mechanisms with large H over R. So like not 0.05 because those vortices are already pretty short-lived anyway. And overall, it's still problematic that it might still be problematic that so few systems have large-scale asymmetries that could be vortices. So yeah, that's my talk. Thank you.
Thank you so much, Michael. Questions? Till, you have a, yeah.
Hi, Michael. So there's an obvious question. Many of the simulations you've shown are, I think, 2D. Is that right?
Yes, they're all of them are 2D.
So how do you think that will change in 3D? And then related, I think there's also a magnetic instability destroying vortices. Do you think that can play a role here?
Yeah, I've started doing 3D simulations recently. So far, it seems like the general trends might hold up. I'm not too familiar with magnetic instability that could destroy could affect things. So, and I haven't been sim doing MHD, so I can't comment on that one. But without MHD, it seems like things are relatively similar. Although I'm still working on that.
We have other questions on the Slack. I don't think so. Yeah, Marcelo.
Hi, Michael. Nice talk. It's Marcelo here. I have a question that I was thinking about PDS 70. That is the only disk that we know it has planets, and there is some kind of asymmetry in the outer ring on top of, in the dust. So have you modeled this particular case and see if you can create this kind of lopsided ring with a vortex that died in the past?
Yeah, yeah, that's a good question. Someone asked me that a few weeks ago, and I haven't tried to model it specifically yet. I think, although I'll note that it is possible to get features like that, or like so like one of the things I showed earlier was like this synthetic image looks like this, but in this case I filtered out the I cut off the dust supply, so that's why you only have this feature. But in general, it does seem more common to have or if you don't cut off the dust supply, then it is normal to expect vortex to be like co-orbital with like a lower contrast ring. It's not really a ring, it's more of like the material that's being funneled into the vortex, like slightly exterior to it. So I would say like those types of structures are like normal. I might expect a higher contrast than what we see in PDS 70. That like the type of like low contrast could happen if like maybe the grains aren't that large, or I don't remember actually if the beam, what the quality of the beam size is. So I'd say it is possible to get those types of features with a vortex, but it's not the like the first type of like it's not the easiest type of feature to get. Yeah.